Optimization. In this section, we will learn how to optimize a given situation given a bunch of information. That may mean something like maximizing profit or minimizing cost or making the largest volume out of a given set of materials that you can put together to create some sort of container, or maximizing an area or minimizing a perimeter or something like this. And this is not to be confused with optimism, like this poor fella down here. Things are amazing, job is good, family is doing well, thumbs up all around. Although I want you to feel happy for this person because this person seems to be doing well. This optimism has nothing to do with math outside of my optimism that you will understand this when the lesson is done. Let's take a look at how to optimize a scenario. The process for optimization can be summed up in 5 little steps. The first of which is to identify all given quantities and unknowns. And in that first step, you also want to draw a picture if it's feasible. In some cases, it might be a little difficult to draw a picture of whatever it is you are trying to, whatever scenario you're given. But if you can draw a picture, pictures always help. That's my opinion. But they always help for me. The second step is to write an equation for the quantity to be optimized. So again, if you're trying to maximize an area, write out that area equation. Or if you're trying to minimize cost, then write out that cost equation. And when you write these equations out, you may end up having an equation that has 2 or more variables on the right side. So what you want to do is to make sure that you can reduce that equation into an equation in one variable. And this may require a second equation or a secondary equation to help you turn the equation into one variable. The fourth step is to determine a reasonable domain, and we will be basically finding endpoints on a continuous interval so that we can go through and then use calculus to solve the given optimization scenario. So again, you'll be checking the endpoints which you get from step 4 and any critical values, again using calculus techniques. You must use calculus for these. You can try to skirt through using maybe the vertex formula for a quadratic if you're given a quadratic function to work with. But using negative b over 2a is not considered to be calculus. So make sure as you're going through these examples or any other examples that you may be interested in trying that you use the derivative to find any critical values on the given domain that you find in step 4. And then essentially we're using the extreme value theorem to find out where the max and min is. Let's look at some examples. A rectangular plot of farmland will be bounded by a river on one side and a fence on the other 3 sides. If the farmer has 800 meters of fencing, what is the largest area that can be enclosed, and what are the dimensions of that rectangle? So the first thing you want to do is write down what you know and what you don't know, but I think the first thing I want to do is draw a picture. Those steps, if you do those, all of that in step 1. So here's my river, and here is the rest of my pen. So a rectangular plot of land. And I want to put fencing around that. I know that I have 800 feet of fencing, so meters of fencing. And I'm going to distribute that fencing over here. So I want to know what is the maximum area. So jumping ahead just a little bit, I know that for the second step, I'm going to I will have to find an area. And generally, the area of a rectangle is length times width. So I'm going to come over here and I've got to have some variables. I can't have an area equation without any variables here. So I think I want to call the length x. So that's x and that's x. And I want to call the width y. So length equals x, width equals y. So the area of this rectangle would be x times y. And this presents a problem because if you were going to find the derivative of this thing, we have an x and a y on the right hand side, we have an a on the left hand side, and this isn't going to help us. Step 3 was to reduce this equation into an equation with one variable. Well, our only choices here are x and y. So we could either have all y's on the right side or all x's on the right side. So we need to maybe use a second equation using what we know right here with the 800 meters, the x length, and the width y. And I think that equation ends up being 800 equals 2x plus y. Now, this is a second equation, a secondary equation, so I'm going to call this 3. And let's see what happens here. You can solve this for either x or for y. It doesn't matter to me. I'm going to solve for y just because that seems like an easier route to go. So this will end up being 800 minus 2x equals y. And you do that so that we can substitute this in for y. So now this step 3, finding a secondary equation, if you need to, I have it here, and solving it for one variable or the other. It doesn't matter which variable you solve it for. And then taking that result and substituting it in to get a new equation of the area equaling x times 800 minus 2x. So now you can see that this entire equation has a's on the right and x's on the left. So really this is acting more like a function, like a of x. The area in terms of x is x times 800 minus 2x. And why don't we make this just a little bit easier on ourselves and say a of x equals 800x minus 2x squared. Right, so just distribute this x through and through. Now we have this equation in one variable. That's awesome. So all of this is like step 3 here. Finding that second equation, substituting something in. So all of this would be step 3. Step 4 is to find a reasonable domain. Well, you know from up here there are 800 meters of fencing. So since we have variables of x down here in our equation, right, a area is in terms of x, what's the longest these x fences could be? Well, since we have 2 of them and we have 800 meters of fencing, and they have to be the same length, I think the maximum x could be would be 400 meters. So that's a maximum value. And the smallest, not that this would be very useful, like 400 meters picture would look something like this. You just have these two, like here's the river again, and you just have these 2 fences coming out here, 400 meters long. There's no area, it's just a line. The other thing we could do is we could try to make x equal to 0, right? That's the shortest distance that could be here. But then that would give you a pen that looked like this. And again, there would be no area. That would just be a fence along the river. You wouldn't be able to grow anything in there. You wouldn't be able to put any animals in that area. It's just doesn't make any sense, but that's the minimum it could be. So hopefully we find a number between 0 and 400. So the final thing is to use calculus. So all of that, there was no calculus done in this entire exercise. We saved that for the whole last step, and we will end up using the extreme value theorem. So check out the equation here, 800x minus 2x squared, that's a polynomial. This thing is continuous. No less, it's continuous on the interval 0 to 400. So on this interval, we are guaranteed a maximum and an absolute minimum. So let's take that derivative and see what happens. We have a prime of x equals 800 minus 4x. And if you set that equal to 0 to find your critical values, then you have x equals 200, and that would be meters. So then what we have to do is we have to go back to our area, and as a matter of fact, I'm going to use this example right here. Since we're all in x's, I want to use the simplified equation with one variable only, and I'm going to test this out. I want a of 0, I want a of 200 because that's the critical value, and I want a of 400. 0 and 400 are the endpoints of our interval, and the critical value that is on that interval at 200. So when you substitute 0 into this equation, you end up with 0. And as it turns out, if you substitute 400 into this equation for x, you'll also get 0. When you substitute 200 into this equation here, you will end up with 80,000. Oops. There is your absolute maximum, right? And that makes sense because we are trying to find the largest area that can be enclosed. That area is 80,000 meters squared. So there's the largest area. And what dimensions give that area? Well, we already know one of them. That was what we substituted in for x. That was 200. And if you want to figure out what y is, we can just come back here to this other equation we figured out in step 3. In fact, the simplify solved equation for y. If you substitute 200 in for x, you'll get that y equals 400 meters. So here are the answers for the area that can be enclosed, 80,000 meters squared, and the dimensions that give that, 200 by 400 meters. Below is a figure of a rectangle inscribed in a triangle with a hypotenuse that is 4 units long. And I also want to point out that right here, this is an isosceles right triangle. So this side and this side are the same length, and the hypotenuse is down here, 4 units long, 2 to the left, 2 to the right. So the task is to find the maximum area the rectangle can have. And there's a lot that goes into this. You don't have a whole lot of information here, but we can figure it out. I'm pretty sure we can figure this out. So let's start here with this point. I see this point right here, and this point can change anywhere along this line. So if we know where this point is, then, and we know the coordinates of this point, we can find the area of this rectangle. The question becomes, what is the point where this rectangle has the maximum area? The maximum area depends on where this point is. That's why it's so important to figure out what are the coordinates of that point. Well, we can easily start out with the x-coordinate x. We don't know what the x-coordinate should be, so we should just call it x. The y-coordinate takes a little more thought. So since you can see that this line from this here from this point on the y-axis over here to the x-axis. I suppose I should give you a little bit more information. This is 2. That the slope between this point and this point is -1. And in fact, even better, the equation of this line is y equals 2 minus x. That's a slope of -1 here with a y-intercept of 2. Then we can figure out what the y-coordinate of this should be. It should just be 2 minus x. That's because, think about it, if this point were at 1, the height would be 1. That's given from this equation. So you have to know how to find the equation of that particular line. So we have this coordinate here, x and 2 minus x. Then all we have to do is figure out what dimensions or what do we multiply to get the area of this rectangle. Let me shade that in. We're trying to find the area of this rectangle right here. Well, it would stand to reason that if you go x to the right, just like this point is given right here, then your height would be 2 minus x. X to the right, 2 minus x. So if you multiply x times 2 minus x, that just gives you this half of the area. If you're trying to find the other half of the area, you also have to go x units to the left. Because of the isosceles nature of this triangle, this point will have the same x-coordinate, well, I should say exactly the opposite x-coordinate as this point. So this point over here would be -x, comma 2 minus x. So what is the area of this entire rectangle? Well, this distance down here is 2x wide and 2 minus x tall. So we were going all around here. This technically is step 3, where you find that other equation. Step 1 was drawing a picture with what you know and what you don't know. And step 2 was to find that optimization equation. So we're trying to maximize the area of a rectangle, and the area of that rectangle is 2x, and we would have just picked y normally, but now we can substitute this 2 minus x in for y to get this. X equals 2x times 2 minus x. The next step is to find the domain. So what is x allowed to be? Since we're basing x on this point over here, only this point, we know that x could start at 0 and go all the way over to 2. So my domain here for x would be 0. The domain would be 0 to 2. That's it. The other point over here is just reflected over the y-axis from this point. So we only need to concentrate on this point over here, and you can only range that x value from 0 over to 2. So the last step then is to use this equation here. This is area in terms of x. Here it is. We can just go through and find the derivative and use our extreme value theorem, because this is in fact 4x minus 2x squared. This is a polynomial again, and it is continuous on the domain 0 to 2. So we can find the derivative. This is 4 minus 4x. And when you set it equal to 0, you'll end up with x equals 1. So there's a critical value. We have some endpoints. So this just uses the extreme value theorem. So we need to find a of 0. We need to find a of 1. That's the only critical value we found. And we need to find a of 2. That is the other endpoint over here. 0 and 2 are the endpoints. 1 is a critical value. So if you substitute 0 in for x in this equation or this equation, either one, substitute 0 in here, you'll end up with 0. If you substitute 2 in there, you'll also end up with 0. And if you substitute 1 in there, you'll end up with 2. So the maximum area is 2 units square. Right, so you need the units over here, 2 units square. That'll be the maximum area because that's the largest number in the list, 0 or 2. 2 is larger than 0. That being said, I guess we answered the question. Find the maximum area the rectangle can have. 2 square units. You've been asked to design a 500 cubic feet square-based open-top rectangular bin. What are the dimensions of the bin that will use the smallest amount of materials? So this is where we need to go through and actually write out a lot of information. The first of which is, what are we trying to find? We're trying to find the dimensions. And we know that there is a volume involved with this. And that volume is 500 cubic feet. So what are we trying to minimize? We're trying to minimize the dimensions. And I guess the smallest amount of materials, what does that mean? I guess we're trying to minimize the amount of material used for the sides and the base of this bin. That means we are trying to minimize the surface area. Can't make a box without some sides and a bottom, without 4 walls and a bottom. So we're trying to minimize that surface area, what needs to be used. So we have some really good information here. Let's come over here and draw a picture of what this looks like. I suppose we have to have a rectangular bin, so we're going to use some sort of a rectangle here like this. Oh, but at least we know that the base is supposed to be square. Let me draw this in here. Maybe something like this. And this is open top. So we only have to worry about 5 sides: the back, the right side, the left side, the front, and the bottom. So luckily we know a thing or two about this so that we can figure all that out. We just have to now assign some variables. Maybe I want to call this square base x and that x. And maybe I want to call this height h. You can pick any variable. You could have picked y here for this one. So what are we trying to do? We're trying to minimize the surface area. Let's see what we can do here. The surface area of this particular box would be, so let's see, this is step 2. The surface area, I'm just going to call SA, is the bottom plus the 4 sides. And all of the 4 sides are the same height. So this side is height h, the front side is height h, the right side is height h, the back side is height h. And when luckily, all of the widths of each of these sides is also the same. All the widths here are x. The bottom in this case is x times x. So we have this equation now. This is x squared plus 4xh. Right? The area of each side plus the area of the bottom. Great. So we have that. This is not going to help us. We have an equation with 2 variables over here, x and h. Maybe we can use something we know. Oh yes, we have a secondary equation. Check this out. we know that the volume is the base of the bin times the height, and that should equal 500 cubic feet. Right, that's given up here with the volume. So we know the volume of this particular bin is x squared h, and it equals 500. Which variable do you want to solve for? We can solve for x, we can solve for h. I'm going to go ahead and guess that you would want to solve for h here. If you solve for x, then you have to take the square root of a side and then tell me if you have to use the positive or negative version. Let's keep it easy and solve for h. If you divide both sides by x squared, you get h equals 500 over x squared. And what you get to do here now is substitute this 500x squared in for h in the equation we are trying to optimize. So when you do that, that'll look like this. The surface area only in terms of x is x squared plus 4x times 500 over x squared. So we can simplify this a little bit. Let's see what happens. If we simplify this a little bit, this will give you x squared plus 2,000 over x. All right, so reduce an x with one of the x's in the denominator, leaving you with an x in the denominator. 4 times 500 is 2,000. Cool, so now we have this equation. Let's go back and look at this to see what a feasible domain is. If we know that the volume has to be 500 cubic feet, and the base is square, then we know that the smallest height this box could have would be 0. It would approach 0. So that means if we wanted to find what are the biggest dimensions for x here, I think we would just have to set x squared, this base, equal to 500 so that we could figure out what that is. So the largest base, so let me do step 4, here's domain. The largest that the base could possibly ever be is 500 square feet, right? All of the surface area is taken up by the base. So if that's the case, the largest it could be in simplified terms would be 10 square root of 5. The smallest that we could have for each side of the base here would be 0. Again, that doesn't make a whole lot of sense, but the domain could actually be 0. All right, so we have a feasible domain. Let's do the calculus part. The calculus here is to take the derivative of the surface area function in terms of x. And when you do that, you get that the derivative of the surface area function is 2x minus 2,000 over x squared equals 0. So right away, I can see that there is a critical value at x equals 0, and that's because that would make the first derivative undefined. So there's a critical value at x equals 0, and that comes from the denominator there. But if you actually solve this equation for x, your first step would be to multiply everything by x squared, or whatever's in the denominator. If you have a different example that you're working through, just multiply by whatever's in the denominator, and that'll give you an equation that looks like this. 2x cubed minus 2,000 equals 0. Then you can divide everything by 2 and solve with a cube root property, and that will tell you that x equals 10. So we have, again, 3 values, even though it looks like we may have a fourth with this critical value. Here's another critical value over here with 10. Then we have to go back and check the original surface area equation, either this one, or I'm going to use the simplified one. As long as it's not the derivative and everything was simplified correctly, we can use this one here. So the original surface area equation, all in terms of x. So I need to find SA of 0, which you can clearly see will be undefined because there will be a division by 0. We need to find SA of, I'm just going to jump to the other end point here, 10 square root of 5. That will give you 500 plus 200 over square root of 5. And that comes by substituting this value in here for x. So that will give you 100 times 5 is 500. That's where this comes from. And then substituting this value in here for x. So the 2000 and the 10 will reduce to 200 in top over the square root of 5. And the last value that you could put in here is the 10 from our critical value that we found. So 10 will go in here for x, and that will leave you, let's write this out here, surface area when x is 10 equals 100 plus 200, and that is 300. This one is undefined, and this is about 589. And since we are trying to use the smallest amount of materials to build all of these sides and bottom, we must use 300 square feet of materials. We can't use an undefined amount of materials, and this is more than 300 square feet. So 589 is bigger. So we pick the smallest number we can, and that's 300 square feet. But you're asked to find the dimensions of this box. So you know x is 10, and we can come right over here to this equation and figure out that h must be equal to 5. So h is 5, x is 10 feet, and there are your answers: 5 feet and 10 feet. Find the volume of the largest right circular cone that can be described in a sphere of radius 4. So first I want to get a picture of here of what that would look like. So you can see a picture here. This is a sphere in white with an inscribed cone, and the sphere has a radius 4. So this pink dot in the middle, I'm going to change that into a white dot so you understand that that is part of the sphere, and that this line is a radius out to the top of the sphere, and that this line here is another radius out to the edge of a sphere. So we have this. Now we just have to figure out how to maximize the volume of the cone. So we have a picture, that's one. We have what we know here, again, that the radius from the center to the top of the cone and the sphere is here, and that distance is 4. And that this distance over here is also 4, from the center of the sphere to the edge of the base of the cone. The next thing that we are trying to figure out is the volume of the cone. That's what we're trying to maximize, find the volume of the largest right circular cone. So the volume of a cone, hopefully you can still remember this from the lesson on related rates, that the volume equals 1/3 pi r squared h. And it is important to keep in mind that when looking at this equation or this function here, that this r is not the radius of the sphere. It is the radius that is down here of the base of the cone. This height is the height of the cone. So in looking at this exercise, we have no clue about the total height of this cone, nor do we have a clue about the radius of this cone, of the base. One last bit of information we know is that since this is a right circular cone, that there's a right angle here. The first step then in turning this equation into an equation in one variable on the right is to identify the height of this cone. And I'm going to call that height, this whole height here. And this whole height, I'm going to call that x. And that'll make us do a little bit of extra work later, but for now, we can start defining these variables on the right in terms of x. So step 3, the height of the cone will be x, and the radius of the cone, which is right here, radius, and we will have to use the Pythagorean theorem to find what the radius is in terms of x. And we're going to use the Pythagorean theorem on this little triangle right here. So r squared plus something squared equals 4 squared, because 4 is the hypotenuse on this little triangle right here. But how long is this distance? Well, this distance is the entire height minus this part here. So what's going in here is x minus 4 squared. So you can see something really cool here is if we can solve for r squared, that's what we need in our equation. So what I'm going to do is subtract x minus 4 squared from both sides and get r squared equals 4 squared minus x minus 4 squared. Then the next step is to say r squared equals 16 minus x squared plus 8x minus 16. And so the 16s will reduce away here, leaving you with an r squared equals negative x squared plus 8x. So now you can see that we can substitute this in for r squared, and you can substitute x in for h, leaving you with this new equation. I'm going to write it in blue, that v of x, because now the volume is all in terms of x, of 1, actually I'm going to write it as pi over 3 because that's the same thing as 1/3 pi. R squared is negative x squared plus 8x times h is just x. So this is the new equation we will be using for this example. And now we can come over here and find the domain relatively simply. The domain here is based on x, which is the height. And so the height of this cone can range from the top of this point, or the top of the sphere, if this height shrank all the way to 0, or the height of this cone could extend all the way down to the bottom of the sphere at 8. So we can have a domain 0 to 8. So now all we have to do, that was step 4, is come down here for step 5, find the derivative of this equation. And for that, I want to distribute this x because using the power rule here would be much faster than using the product rule. So I'm going to have v prime of x equals pi over 3. And this ends up becoming in here, in a set of parentheses, negative 3x squared plus 16x. And if you set this equal to 0 and solve for x, you'll see that x ends up equaling 0, or x will also equal 16 over 3. So here we go again. We have to use this equation here, all in terms of x, because that's what we have answers for, x's. So we have to come over here now and figure out what is v of 0 what is v of 16 over 3, and what is v of 8. And v of 0 is, in fact, 0. V of 8 is also 0, which means v of 16 over 3 will end up being our answer. You can't have a smaller volume than 0. So this will be the answer. And that means you have to substitute 16 over 3 into all of these x's here, and then multiply by pi over 3 to get the final answer of 2048 divided by 81 times pi units cubed. That is a very horrific looking answer, but it is an answer nonetheless. Time for one more example. The USPS will accept a box for domestic shipping only if the sum of the height and the perimeter of the base does not exceed 108 inches. What dimensions with a square end will yield the largest volume? So in this example, I think it would be best to see a picture before we do anything else. Here, a box could look like this. And what we know is that the height of the box, or this side here, and the perimeter of the base, this here, cannot exceed 108 inches. That means it has to be less than or equal to 108 inches. So since we know that the box has a square base, that means that length is x and that length is x, we can call this distance here y. And the lengths y plus 1, 2, 3, 4 x's equals 108 inches. So that's all we know for step 1. Step 2 is write down the equation you're trying to optimize. So we're trying to optimize volume, and for this box in particular, it would be x squared for the base times y, which would be the height. So x squared times y, length times width times height. So now the goal is to get this equation in terms of one variable. So that's step 3. We can have this equation, right? That's the secondary equation, y plus 4x equals 108. And I'm going to solve this equation for y, which will give me y equals 108 minus 4x. And then I'm just going to take this portion and substitute it in for y in that equation, giving me a new equation, all in terms of x. So the volume in terms of x is x squared times 108 minus 4x. Step 4 is to find a reasonable domain. So here's step 4 with the domain. Well, we're looking at x, right? I have volume in terms of x. So that means I need to come over here and see what's the largest x could be, or the smallest x could be. Well, if you shrink x all the way down to 0, all of your 108 inches would just be in a single line. So I'm going to state that 0 would be the smallest. And if you evenly distribute 108 inches to 4 different sides of the square, you would just end up with a flat square being having a side of 27 inches. So we're looking for numbers between 0 and 27. Now when I go through and find this derivative of v of x, the volume in terms of x, I want to make this distribution here, because distributing a little distribution like this and using the power rule is faster than using the product rule here and trying to simplify. So the derivative v prime of x equals 216x. That's what you get when you have 108x squared and you use the power rule. minus 8x, I'm sorry, it's not 8x, it's 12x squared. So multiply x squared here, that would give you 4x cubed. Bring down the 3, 4 times 3 is 12, leaving you with an x squared. Cool. Now we just have to set this part of the derivative equal to 0 and solve for x. And as it turns out, you can factor this. You can factor out a 12x from both of these. And I know this term pretty easily, that leaves you with x, and this term leaves you with an 18. So it would be 18 minus x equals 0. This factor tells you x equals 0. This factor tells you x equals 18. So then we just have to use the extreme value theorem to find the max and the min. It's just v of 0, that's one endpoint, and a critical value as well. So we just figure that out. It is 0. You can see that if you substitute 0 in here, you'll end up with that. The other endpoint, v of 27, also equals 0. That comes from this 27 over here. 108 minus 4 times 27 gives you 0. So 0 times this thing, whatever it is 0. The only other number we have left is 18, so I'm guessing that has to give us the maximum. So let's see what that is. V of 18 will be equal to 11,664. So this x is our answer. And let's see what we're trying to figure out. We're trying to find what dimensions of with the square end will yield the largest volume. So we know x, these dimensions here will be 18. So that means this side will be 18, this side will be 18, this side will be 18, and this last side will also be 18. And that eats up 72 inches of what is available. So when you have an 18-inch square, that takes up, let's see, times 4, that is 72. If you take that away from 108, you end up with 36 inches for y. And again, that equation is right over here if you're trying to solve for y. So 108 minus 4x, that's what we did. We had 108 minus 4 times 18. Y is 36. So you want dimensions that are the base of 18 inches by 18 inches and a height or a length or whatever you want to call it of 36 inches.